Welcome back. So in this video, we'll continue talking from section 1.2 and get into what's known as Gaussian elimination. Gaussian elimination really means that we are going to reduce a matrix all the way to row echelon form. We can talk also about what's called Gauss-Jordan, which is really we're trying to get it into row reduced echelon form, but usually just for simplicity, I will say Gaussian elimination, which means row reduction. You can simply interpret that. So let's look at this specific example. We want to row reduce it. How can we go about that? So I want you to pause the video and think, what is the first step that you would do? All right, so if you did that, I'm going to show you my first step. Again, there's actually multiple ways to get to row echelon form. So personally, I would swap row 1 and row 3. Excuse me, row 4, it's a typo. So notice I took my final row and my first row and I swapped them. So again, let me just make a quick little note. That is supposed to be row 4. So if I do that, now the really nice part is now I have a 1 in that first spot. It doesn't have to be a 1, but 1s are really nice because we multiply them and get everything. So for row echelon form, I have no rows of zeros, but I do need to eliminate both of these elements right there so that they are both zeros. So what steps would we take, or would you take to do them? Go ahead and pause the video and perform those steps. All right, so if you did those, personally, I did row 1 plus row 2, put that back in row 2, and we got, as you can see, of 2, 0, 2, 4, negative 6, negative 6. Again, I just did row 3 plus 2 times row 1 into row 3, and we get 0, 5, 10, negative 15, negative 15. Now, what we're sitting here is our whole first row is all zeros. And for sake of space, let's go ahead and reset this so we have a nice clear spot. All right, so if we're looking at this, as I said, my first column is now exactly what I want it to be. I got a 1, I got a bunch of zeros. So now I come down to my next. Well, my next leading entry would have to be this right here. I can work with a 2, but as I look at this, everything in that specific row is even, which means dividing everything by 2 would actually give me a 1 right there. Again, you don't need 1s for row echelon form, but 1s are the easiest terms to use in general when it comes, especially if everything's scaled like this. So if I take row 3, in this case, I can take row 3 multiplied by 2, and then take row 4 multiplied by 2, and then I can actually then start scaling. So row 3 minus 5 times row 2. Again, there are multiple ways you could do it. You could have simply divided that entire row by 1/2 and then added, or in this case, I can scale. There are multiple attempts to do these things. Again, they'll all get in the same spot. Looking at this, my 2 scalings that I did, these first 2, so in this matrix where I scaled row 3 and here where I scaled row 4, and then when I added row 3 plus 5 times row 2, because obviously 5 times this added down 5 times, hey, look, they're all 5 times each other. So essentially it's going to give me a row of zeros. Well, we could now be like, well, let me swap that row of zeros with row 4, but I would hold off personally. I would hold off because we don't know if that's what we're going to end up with. What if the last row ends up being 0? Then I swapped just so I didn't need to. So instead, I am going to say, let's just work on getting rid of that negative 6 in row 4 by 4 plus 3 times row 2. And suddenly that gives me this. Now notice that this row, our final row, is now not all zeros. So I do need to swap those 2 rows to be in row echelon form. So I swap them. And now let's consider our specific situation. Where are our leading entries? We will get to this later on. We'll actually call these pivots. That's another term that I like to use. Then go Googling. So this is my first leading entry. This is my next leading entry, and here's my third leading entry. And notice they move to the right as we go. Secondly, they all have zeros directly below them. So I have all zeros, all zeros, all zeros. So because of that, we are in status, and the only row of zeros is in the last line. We satisfy the three conditions of row echelon form, and thus we are done for row echelon form. Now, again, you may have come up with a slightly different version. Like if you had, I mentioned that we could scale, we could divide this entire second row by 1/2. Because of that, you may have come with a slightly different row echelon form. This is because there are multiple versions. But there are some things that later on we'll get to. That row echelon form does give us some partial information that I'll mention. So my matrix A, the row echelon form is, as we have. All right, let's get to a second example. Here's matrix B. I want to row reduce it. So I want to get this all the way down to row reduced echelon form, or REF. All right, I want you to pause the video and try to do your specific order of steps, and then watch mine. They may come out slightly different, individual steps, but I want you to think about it. So go ahead and pause the video and try doing this one yourself. All right, so if you did that, the first step that I personally did is I did row 1 and row 3 swapped. Next, I did row 2 minus row 1, because that would make that 3 go away. All right, at this point in time, you might notice, let me grab a highlighter, my whole first column has a pivot or a leading entry and then 0 below it. That is good for row echelon form. I don't know if I like that in general, but we'll have to take that in consideration. But I'm going to leave that for right now. And as I do my second step is I'm going to scale this second row. So as you again notice, the second row is all even, so I can divide by 1/2. Because our eventual goal is to reduce row echelon form, all of our leading entries will have to be 1s. So we might as well go ahead and do it at this step. If I do it, you'll notice that gives me now a 1, which means when I want to eliminate this 3 that's below it, it's going to be much, much easier. All right, so let me give myself some new space. My next step is then obviously I took row 3 minus 3 times row 2. And the result is going to look like this. Now notice I have a leading entry of a 1, I have a leading entry of a 1, and I have a leading entry of a 3. If you look at this form right now, it's in row echelon form. So we're partway there. We have to accomplish those last 2 steps, which are all the leading entries must be 1s, and every entry in the column of a leading entry must be 0 except for that 1. So what does that mean? Let me change colors real quick. That means that I got to get rid of this 9. I got to get rid of this 1 and this 6. So all those in blue, I have to eliminate. If you're colorblind, I apologize. The ones I just highlighted are that. Another thing that I do need to do is that this 3 right here has to turn into a 1. So you can do these in multiple orders. Personally, I want to eliminate this 1 first by taking row 2 minus row 3. Now notice what that is essentially I'm going to add up. So while we've been adding down previously, I'm now adding up. That makes that a 0. Okay, that's nice. I would like to get rid of this 6 here. And so what I did is row 1 minus 6 times row 3. And so now I have a column that is a 1 and all zeros, which is super nice. So that leading entry, all taken care of. All right, let me clear that. Now, there are multiple steps you could do here. I personally did row 1 plus 9 times row 2. Looking at this, that's when I created this slide. Looking at this now, the second thought, I might just scale row 1 by 1/3 instead at this point. But I made that decision when I made the slide, so I'm going to go with it. Keeping along those lines, you multiply all of row 2 by 9 and add it up, and I get such. The major downside being I now have a really big number over here. But 3, -6, 9, and 72 are all multiples of 3. So I can divide the whole first row by 3. And now, if you look at this final version, I have a column with a 1 and all zeros, column with 1 and all zeros, and a column with 1 and all zeros. Hence, this is my reduced row echelon form of my matrix. All right, now, one final thing to talk about, and this is a kind of nice thing. So let's go back to augmented matrices. Notice everything I did today was without augmented matrices. But if I have an augmented matrix and I end up in this form where you'll notice it's reduced row echelon, because I'll notice I got boom, boom, these are leading entries. There is no leading entry in this last row. Well, what does that mean? This form, as a reminder, meant that if I turn this back into a system of equations, it looks like this. But I can't really substitute back in because now I have a system with 3 variables and 2 equations. That means there actually are infinite solutions. We actually can talk about what are those solutions. So what we can do is I can actually literally solve every single one of them. So x1 is in terms of x3, x2 is in terms of x3, and then x3 is what? Well, x3 is what's known as our free variable. So I can literally, if I wanted to, call this t, and then I can scratch out this where I have x3, and now I have t. Now, this then ties back into what you should have learned in previously in some calculus classes, where we learned some parametric functions. This is where we get to use parametric functions essentially. So our system, our general solution is any x, we pick any value t, pick any real number. And then we take that and plug it in up here and we get our x1s and x2s. So x3 is kind of our open variable and x2 and x1 are based on x3. And this idea is how we solve general solutions. Now, here is a final theorem to kind of tap this off. You can read through all this, but what it says essentially is that if I end up with a final row that's all zeros except for the last term is a b, there's no solution. If there is any row of that form, then we have a problem. But if any row looks like that, there's no solution. Otherwise, it has a solution or infinite solutions, in either case. I hope that helps. Please let me know what questions you have, and good luck.